Now, assuming this will work, I will start with, what is this? This is different. Okay. No. Okay, so apparently the sidebar does that. Um, so I'll share this PDF, but I just wanted to point out that okay, the screen recording is ongoing. So I will share this PDF of my notes. I think I shared a location. I haven't updated it in a while, but I will do that. The point I was referring to was this question of what this means and the O of h square and all of these terms. Slightly different proof, but in the end you can rearrange it to get this order of terms. It's at, okay, my notes have not synced, but there will be oh yeah, there is a URL here. It's a nice proof. It's basically the theory of kernel density estimators. Like the Wikipedia page had the final sort of um, final proof, a final line of the proof, but this has the entire proof. I don't know if this will. I don't know if my screen share will capture this. Can you guys? Oh, you guys, I haven't shared screen. Guys, you have to tell me this. What? Okay. Is my screen share visible?
Yeah.
Okay. If I'm like interrupt me, tell me. Um. Okay. Anyway, this is basically the proof for the KDE stuff. Um, Slightly different. Like I said, he doesn't take it as weight times yi. He takes it as the bias of this estimator, which means the expected value minus the true value, and then he solves for that, and he gets a term which is similar to basically what we're talking about. Um, P of x, P dash of x, P double dash of x, and O of h square. That sort of arrangement of terms. Um, yeah, and the things get cancelled out, and eventually you end up with what we think we needed. Um, but that's at least that will tell us something about how to solve this kind of problem in the way Shaliji says. I haven't looked at this in detail, which is why I don't have the exact proof, but I just wanted to point out that okay, I did come across this and it seems reasonable to um, extrapolate what he said based on these kind of proofs. Anyway, back to the topic at hand. You can see this notability thing, right? The notes, guys.
Yeah, like we can see your screen. Yeah.
Yeah. So chapter 5 simulation. That's where I'm at. Um, Assuming you can see that too.
Yeah.
Yeah, you were right. It's a pretty simple, straightforward chapter, so we can breeze through the details. Um, in general, so far we've talked about quantifying uncertainty, and we need the true distribution, or to be more accurate, the sampling distribution of things like estimators. There are very strong simplifying assumptions that often do not apply. So then there is little hope of writing down these distributions in a closed form, but at least what we can do is sample from these distributions. And this really like messed with my head originally when I was talking about like how do you sample from a distribution without knowing what is going on. Like if you can't write it down, then how can you code it up? That's what I used to think. The idea is you can use one random variable to represent another random variable and then modifications of those and ultimately arrive at the distribution, except without explicitly writing it down. So that's the general idea with sampling. Um,
Swapnil, on that point, you mentioned that we can use one random variable and use transformations to get a new random variable,
yeah.
right?
Mm-hmm.
But unless we know what the final function should be, like if we know that in a linear regression, the function is y is equal to beta naught plus beta 1x.
Mm-hmm.
So in that case, we can apply a transformation which will be basically adding beta naught and multiplying it by beta 1.
Mm-hmm.
But if we don't know what the final function should be or what the final form of the function is, how do you transform it? Like even in the examples which they have given, they know that they want to transform it to a Gaussian or they want to transform it to a different function. So if you don't know the final form, you still won't be able to transform it, right?
So when they say you don't know the final form, they mean you can't write down a closed equation for the final form, which means it's like too complicated to calculate, that sort of thing. But it is not too complicated to approximate.
Oh, okay, okay. But
So
even for an approximation, you would need some sort of closed function which would be an approximation.
yeah, and that is not difficult to find. So approximate functions are not that difficult to arrive at. And then how good that approximation is, what is the quality of that approximation or the error that you estimate from that approximation and the true function. Those are the sort of things we look at. And ev- at least a lot of places where you say the true function, it's you don't actually know the true function, but you have some true values that come from those functions, which you call samples. But that's
Yeah.
the idea. You use those samples to estimate the quality of your estimator,
Okay.
to check the quality of your estimator.
Okay. Yeah. Yeah. I got you.
So I like the way he writes about this. A mathematical model is a story about how the data could have been generated. Simulating the model means following that story, implementing it step by step in order to produce something that looks like the data. Sometimes we call it synthetic data, sometimes surrogate data, or surrogate models also, or a realization of the model. So there is an inherent stochasticity in the sense, even if you start with the same inputs, it is not necessary, or it is in fact unlikely that you will arrive at the same outputs, because something random happens at some step and that means it won't really repeat. But it does mean that there is some sort of pattern over like millions of times of repetition of the same thing. So um, just as a side note to keep that in mind. So the model specifies a distribution over the realizations, and doing many simulations gives us a good approximation to this distribution. So some example is described where if you have x1 which is drawn from a Gaussian with mean mu1 and variance sigma square 1, um, you have another Gaussian mean mu2 sigma square 2, and you have a third Gaussian. You know that the distribution of this x3 will be look like drawn, like it's drawn from a Gaussian of mean mu1 plus mu2 and variance sigma square 1 plus sigma square 2. So you know that this happens. So there are two ways of getting x3. Either you simulate x1, simulate x2, add them to get x3 and do this millions of times, or you simply use your math to calculate this and to calculate this closed form equation for x3 and then draw samples from this x3. So that's what they're saying, that sometimes this writing this down explicitly is not possible, but we do have x1 and x2, so we can use these to generate x3. Yeah, that's basically it. That's the difficulty with simulation, the point of simulation. um how do we simulate stochastic models? Chaining together random variables. I feel like we covered this because he's saying the same thing essentially, except this time he's using conditional distributions, which is, I mean, technically the same thing. Like this is x3 conditional on x1 and x2 is drawn from this. So just another example, y conditional on x is drawn from a normal distribution with beta naught plus beta 1x as the mean and sigma square as the variance. So something like this line as the mean, and because of this variance the final distribution of y is likely to look something like this red curve. At least I think this is the case. If I'm wrong, please feel free to correct me. And x is drawn from a uniform distribution between x min and x max. So typically you don't just have x and y, you might have like 1,000 variables in the middle. So the simple way of doing this simulation is start drawing from sequentially each of those variables. So if there is a to z as the sequence of variables, then you simulate a, you draw a sample a from some distribution that is given to you. You draw b conditional on a from the distribution that you have for b conditional on a, c conditional on b, d conditional on c, and by that you implicitly mean d conditional on c, b and a because you've drawn both b and a also. But you don't have to write that explicitly because it is implied. So in general, you'll see how you arrange the variables in complicated probability models in a natural order, so that we start with independent exogenous variables, which is not relating to the structure. Exogenous, I forget. Maybe I can do this. No, no three finger tap. Okay. I'll look up the exact definition of exogenous because I don't want to be wrong about this. Give me a second. Relating to or developing from external factors, I see. Okay. So, yeah. Basically, A is not dependent on any of B to Z. That's why you can start with A. And there might be similar other variables that you can start with. So that's the point. You start with those so that you have some value, and then you can condition the dependent variables on these values of these independent variables. Right. This is the natural order for simulation. Okay. Then we have random variable generation. R provides. Oh, okay. It's talking about R. So the motivation he offers is we have these libraries that generate random variables, but we don't really know how it generates these random variables. So let's open up this black box and try to understand what these libraries do. And so he says essentially these transformations often rely on transforming uniform distributions into other distributions. And this is something that's also covered in Carlos's notes in a nice way. I can link you to the exact, yeah, I'll link you to the exact chapter and details. I'll add that here. Let's write that down to remind myself to do that. Okay, that's on the side. So in essence, if we can generate a random variable z with some distribution and v which is equal to g of z, then we can generate v. It's like a building block. Like one block, if you have the foundation, you can build the next one on top of it, and the next one on top of that, and the next one on top of that. And here by on top of, we are referring to conditioning. And So one example given here is if you have z drawn from normal 0 1, then you know that you can transform one normal distribution into another normal distribution by using this sort of um, transformation. I, I, I would say linear transform of z. Um, Linear versus affine, we went over this. I don't remember which one to call this, linear or affine. uh, should look that up. But yeah, we can generate chi-square random variables with 1 degree of freedom as using z-square. We can generate chi-square random variables with d degrees of freedom by summing d independent copies of z-square, so on and so forth. So if you can do this for one distribution, like what is the extent to which you can do this for varying distributions? So suppose that we know the quantile function qz for the random variable z, and we want the random variable z such that the z0, like this is just explaining the quantile function here, um, and in general qz is bigger than or equal to z with probability p. Okay. The quantile function comes as a pair with the CDF, since quantile function is the inverse CDF, um, if which means the CDF is continuous and monotonic, non-decreasing. To recap, the cumulative distribution function was the sum. I thought I wrote this down. Maybe not. The CDF of a random variable x is the sum of probabilities for x. I have to use. I should. I don't.
You have written it here that probability of x is less than equal to a.
Oh, okay.
That yeah.
Yeah. That thing. Okay. Thanks. Um. Yeah. Okay. Fair enough. And the quantile at CDF 0.5 is the median, or the CDF of 90th percentile of the data means that zero point 0.9 with zero point 0.9 probability, all of the data, the if you sample a value of x, it will be less than a. Did I use a here or did I use p? I didn't actually use it. I used 90th percentile. So if this is p, then p will be greater than 90% of the data. That's essentially what these two equations are saying. Again, this is like, I may be wrong here. I don't think I am, but please read this carefully, because it's very simple, but it's also like very subtle, and they go from like a very simple case to a very complicated case very quickly when people actually use this in practice. So it is very important for these two equations to be like clear for you. So in the quantile method, quantile, like I said, is also the inverse distribution transform, like the inverse distribution function. In this method, you generate a random uniform random number u, so u is drawn from the uniform distribution, and feed it as an argument to qz, the quantile function. Now, at this quantile function of u has the distribution function fz. So the CDF is fz, which is the inverse quantile, and so the probability of qz at u is the probability that qz at u will be less than or equal to a value a is the same as the probability, because this is a monotonic non-decreasing function, which means side, yeah, a monotonic non-decreasing function, which means ah, arey yaar. Because of this, at every point we can define a unique inverse. That's what this monotonic non-decreasing means. Like at no point will this, again, new color, at no point later will this dip down again, such that there are, at this value, there are two inverses. uh, so if this is y and this is the plot of f x, this is x1, this is x2. I'm drilling this down because this comes up a lot in different contexts, and it's important to know what they mean by a unique inverse and monotonicity, and like what is this. So if you're defining as y is equal to f under capital X of x1, then if q is equal to f inverse, then q of y is equal to x1, right? But now if you don't have this non-decreasing and this thing later, okay, I should again switch colors. I shouldn't have used pink for all of that. Anyway, the point is, if this decreases later, it is not non-decreasing. Single line. Okay. If this decreases later, then now this q of y can be x1 or x2. So that's the point, because y is also now equal to fx. So then a unique inverse is not defined. So that is why this CDF being a non-decreasing function is important, because you don't want this and you want a unique inverse to be defined. So yeah, hopefully that explained something you will be using in the future. So yeah, these two conditions are important, because even in the last line they use a condition similar to that. Sorry, the last line they use the fact that u is uniform, and if a uniform value for a uniform function between 0 and 1, or between a and b, let's say 0 and a, the probability that you're going to sample a value x less than a, or let's use this definition, the probability that u is less than equal to a, fc of a. Because of this uniform probability, once you start adding up probabilities below it, it adds up to fc of a anyway. Um, yeah, I don't think I want to say anything more about this. And then they take an example of, okay, if the CDF is of the exponential function is this, then the quantile function becomes this, and that's essentially how our exponential works. continuing along what we were discussing, um, the standard. Oh yeah, the standard Gaussian does not have a closed form for its quantile function because if you expand the normal distribution, let's say 0, 1 for the standard Gaussian, you get something like exponential, some constant term here, 1 by root over 2 pi epsilon naught, exponent minus half x minus mu the whole square by sigma square. So this thing does not have an integral form. Like if you try to solve this from 0 to infinity, you won't get an answer. You'll be reduced to something called gamma functions, if I'm not mistaken, gamma or error functions. But yeah, this is always a practice. You should try it out and see where it fails and why this is necessary. Um, and because the CDF does not exist, the quantile function does not exist, which is the inverse CDF. But there are fast and accurate ways of calculating it numerically. Like you can start sampling. No, actually, I will leave this to you to figure out what this statement means and get back to me with like examples or like it's a very popular thing, so you will easily find it. Just Google it. But it's important to know like what this, and this also goes back to your original question of okay, how if you don't know the closed form, then how do you calculate it? And this is the answer to that question. So look it up and tell me what you arrive at. Um, Again, since the distribution function is the same, we can use the quantile method as long as we can, and by this calculate, I believe he means approximate. I mean, I don't know if, so this numerical and this calculate, I guess that's why that works. I don't know. Anyway, if you find QZ, you can get the transformation using the same method that you relied on above. Okay. Um, Sampling. A complement to drawing from given distribution is to sample from a given collection of objects. So the discrete version of sampling from a closed set of objects. I don't know why I've written all of this here, but maybe I was trying to explain what a quantile function is without actually um, relying on the context. But okay, this is essentially from Wikipedia. Um, but I guess we've already been over it. Bunch of this is related to code. It's fairly obvious, straightforward English. Sampling with replacement, sampling without replacement. Why sampling without replacement? You can't sample more than the number of items. Fairly straightforward. If you have questions, please feel free to interrupt. That holds always for all lectures. Okay, seeing none. Move forward. Sampling rows from data frame is essentially the same thing, except this time you pass a data frame as a parameter and the row number. Anyway, you can read that on your own time. Multinomials and multinuis, I didn't know about these before a couple of months ago, so it's interesting to look up what this means and how you use a Bernoulli to sample this and a multinomial to sample this binomial. Nothing out of the ordinary. Probabilities of observation. Often our models of how the data are generated will break up into two parts. One model is, oh yeah, okay. One model is of, like, the model relates to two things. One is how actual variables are related out there in the world. I don't know why I drew that. Out there in the world, and the other part is how variables came to be recorded in our data. So whether, like, to take a good example, oh, he's given us an example. How one might model education and racial categories, relationship to occupation, and occupation relationship to income, versus how we might model the probability that someone appears in a survey as a function of race and income. So this also somewhat relates to, like, exogenous variables versus the variables that you model within, like, your probabilistic descriptions. Hmm. Basically, like, this section will come into picture when we talk about causal inference. Um, like,
In some ways, he's talking about fairness, right? Like what we normally say fairness in machine learning. That's what he's talking about, right?
correct. So um, again, fairness has a lot of causal relationships. Um, and yeah, we'll dig a lot deeper in that when you get to causal inference, but for now it's not that relevant to the discussion. But all he's trying to say is you can't model everything, so there will be factors that you have not accounted for in your model, which is why you can't say that. Will you have to say that under some assumptions this model is what we think of the real world. So those assumptions are not necessarily always true or correct. And repeating simulations, again he explains code related nuances. um, yeah, I don't think there is anything very critical here. Monte Carlo simulations are important, and it relates to the central limit theorem. So what he says is, if a stochastic model gives some distribution of a random variable z, which in general is a complicated object with lots of interdependent components. So you might have x contributing to z, you might have y contributing to z, you might have a contributing to x and y, and all you have is this final z. Okay, and what we are interested in is some complicated function of g, um, which, such as the ratio of two components of z or some non-parametric curve fit through the data points. Anyway, bottom line, we have a complicated distribution for z. And we want to how, what do we know what the model says about g. um, what was g again? We understand a model by saying that it predicts what variable we care about relationship. The model we can simulate how we can run model, so what happens some random variables which are completely theory of components. We may also be interested in some public functions. I think the point he's trying to get at, just if you have different samples and you want to know what this model says about some complicated function g on these samples, just take these samples and run them through this g and observe what sort of result you end up with. So that's like the simplest possible explanation of what he's saying. and once you get these out of G, then you can use your what is the law of large numbers, and we say that 1 by b summation from I to b, and he's cleverly not used n here to not confuse us. B can be any number of simulations, and you know that this will be the expected value, well, will tend to the expected value of G. So we will know at least on average what the model says about G. So this model might be what test scores for some students based on some socioeconomic factors, and we want to know how this affects employability. So you generate these test scores, plug them into your employability tests or whatever, and ultimately arrive at whatever your expected value of employability is. So that's, I don't know how accurate an example that is, but that's the example I came up with in my head. Okay. And we can, in the limit of a large number of samples, you also know that the central limit theorem can be applied to say that this will approximately represent a normal distribution centered at expected value of gz with a variance equal to variance of gz by b. So that is something you can say in the limit of a large number of samples. In general, I think this is the point he's trying to drive at. We can get the whole distribution of any complicated function of the model that we want as soon as we can simulate the model. That's it. Checking the model. Exploratory analysis of the simulations and data. Yeah, this was interesting, right? So, if the model is right, then it represents the mechanism which generates the data. Which means if we simulate, or when we simulate, we run this mechanism, and the surrogate data that comes out of the machine should look like the real data, which is fair. More exactly, the real data should look like a typical realization of the model, because if it does not, then this account of the simulation mechanism might be wrong. So he's taking the original data for the Geyser dataset plus the OLS regression line. This is the line that you learn with OLS. Now we'll consider general tests of regression. Sorry, that's chapter 9. For now, we'll focus on the way OLS is presented as part of a stochastic model for the response conditional on the output with Gaussian homoscedastic noise. So Y, W is equal to beta naught plus beta 1 D plus epsilon. W and D are our response and predictor variables respectively, and epsilon is noise drawn from normal 0 1, normal 0 sigma square. Okay, so we fit the data, we get our OLS. Now we want to compare or check the model. How well does OLS do? A useful principle for model checking is that if we do some exploratory data analysis, doing the same analysis to the realizations should give roughly the same results. This is a test this model fails, because if you look up figure 5.2, which is here, the sort of curve produced by the original data does not match the curve produced by the model. So yeah, um, this tells us that the actual density of waiting time between eruptions dot W, and that produced by the WOS. I think I should say F because there's an actual density of W, and WOLS is the estimate, so this should be does not match. I think this is the right technical way of writing it. Yeah, so here they just use histograms. Um, sensitivity analysis. We've talked a lot about the Gaussian noise assumptions, but there are many others. For example, if we have missing values and we ignore the missing values stating that they're just missing at random, then you're explicitly assuming that these missing values are not representative of any patterns, and that is important. That's not it's not a trivial assumption to make, because if you have a lot of missing values, then it's clear that you might be missing some pattern. What else do I want to say? Um, Not much. I feel like this is fair. Yeah, in general, sensitivity analysis forces you to violate your assumptions and then still check how much the model actually sticks to what you predicted. Which means it checks how sensitive your model is to your assumptions. So that's yeah, how sensitive our inferences are to the assumptions. And it's hard to do. It's not easy to violate your assumptions, then simulate the data, then check how well you actually did. Um, oh, okay, he says it's pretty easy to simulate a model where the assumption is violated. Interesting. I didn't think this was the case. Okay, maybe this needs more thought. I don't know if that's a general statement you can make. I think in real world examples, I guess I don't have enough experience to say, but in toy example, it's definitely easy to violate your assumptions. Like the IID assumption, for example, you can just violate that by sampling sequential data or sampling without replacement or something like that. Um, oh, and that's about it. That's the chapter. Um,
Even for a real world example, like the common example is housing prices, right?
mm-hmm.
And if we are making an assumption that if we are saying that depending on the housing prices, we are trying to predict the quality of education in that area, and if we use some factor like we say the race doesn't matter or something like that, and we only pick samples to check that assumption, we only pick samples from an area where there are only white people or there's only people of one race, then maybe we could we'll be able to check the assumption accordingly whether a final analysis is matching with the original data.
That's a great example. Yeah, yeah. You can easily stratify and check if those change for both sets of people.
Yeah.
Fair enough. Yeah, I'm looking forward to the next chapter. Right, it gets more and more interesting with each chapter. Um, I don't think the question really has any discussion. I might have to do some R programming in one of my courses. I'm seeing if we can do Python, but if not, then at least I will have more context on doing all of these. We did find notes. I sent a link on the channel about another CMU professor's notes using Shalizi's draft book chapters, so that might sort of simplify some aspects for us, especially for future reference. And I hope this session was recorded. Time to check.
Okay, I see what you mean. I see what you mean.